Hi everyone, thank you for clicking. We are sitting here in the reverb chamber at...
We are. You can tell from the lights.
Yes,
Yeah.
that we made. And we wanted to discuss chambers and how we learn more about them. So, how did we first learn about the appropriate method of testing?
Right. So the idea was, in order to test these meters that we make, Safe & Sound Pro 2, the classic meter, we have to have a controlled RF environment because the world around us, in most places in a city, are noisy. When I say noisy, there's lots of sources of RF: cellular, telephone transmitter base stations, people's Wi-Fi routers in their homes, people's cell phones themselves.
And not just at one frequency, but multiple frequencies, multiple
frequencies.
Power levels.
So we need a controlled RF space. Right?
And it's not just how many sources, it's how they interact with one another and how you interact with them that you also need to account for.
Right. So if we're designing a meter that's going to measure RF power, we need to obviously test in a place where there is a controlled known amount of power at known frequencies, or being completely quiet. So we know about Faraday cages, right, which is a completely shielded place. Maybe you can put one of those Faraday cages up in the video. So that's fine, but it's got disadvantages because RF reflects all over the place. So my previous experience has always been, when you do RF testing, we go into what's called an anechoic chamber, RF chamber, and it's got all these absorptive tiles or cones on the wall and on the ceilings and coming from the floor. We've been in some big chambers, and they look really cool. For someone that's ever been in an acoustic anechoic chamber, it's like sound gets absorbed by the walls and floor and ceiling, and it feels like your head is turning inside out. So we want it's really cool feeling, by the way. And most people can only last a couple minutes in there without going like, get me out of here. But RF anechoic chambers are really cool because they have those properties, somewhat acoustically, but more so at RF, that any source of transmitter source, let's pretend that this is a vertical radiating antenna, anything that gets radiated is going to go out into space, but it's not coming back, no reflection. So that has advantages for testing because we then don't have to consider reflections coming from different directions, which can interfere with what the test result is. If our antenna is here and we're measuring here, well, we know in an anechoic chamber that what we're seeing from this antenna is from the antenna and nothing else. And it sounds great. And that's been how we test. That's how other people have tested traditionally and all those things, and I've never thought anything of it.
And because anechoic chambers are more prevalent and...
Yeah, they're around
and
more.
And they're used for other types of testing.
Right.
So we're sitting here in a reverb chamber. Why is that?
Yeah.
Why did we build a reverb chamber instead of an anechoic chamber?
Right, so that happened at one of the RF labs. We've tested our equipment at multiple labs, and one of the labs that I tested in, the engineers there were just like, you know, this is really cool what you're doing, but why aren't you testing in a reverberation chamber? And I said, what? I mean, I knew about reverberation chambers in the use in acoustic and in music for simulating, you know, reverberation drums and stuff. It's a whole other thing. But I never made the analogy to RF, and I asked, it's like, how does that work? And essentially, it is a reverberation chamber is a Faraday cage, but with a couple little additives. And what we're seeing right now, you'll notice the lights changing. It's not that we're sitting here in a place that has rotating beacons like a nightclub or something like that. We're seeing the lights reflecting from what are called RF stirrers. And Kayla can show some pictures of RF stirrers from typical reverberation chambers. You know, they're shaped like, you know, folded 90-degree folds. Accordions. There can be different stirrers. And what's happening is that we've got the benefits of a Faraday cage or a anechoic chamber being completely shut off from the world. Right now, this room that we're in, there is no RF getting in or out of this room. The only RF, there's a little bit coming from the GoPro camera that we're using to film this video, but there's no RF getting in or out, so we've got a quiet environment. Now the problem with the Faraday cage is that RF is reflecting from everywhere, and if that reflective nature of these walls are fixed and it doesn't change, well, you don't know. Remember I said here, let's say this is our transmitter antenna and this is our unit that we're testing. Well, if I happen to have it in one location that's got a lot of reflections that that coincide with each other, in other words, constructive interference patterns, it's going to create a higher reading level than a destructive one. If I moved it, let's say depending on the frequency, if I moved it just even a few inches, depending on the frequency, like when we're talking 6 or 8 gigahertz, a few inches is a huge difference. I mean, wavelength at 10 gigahertz is 2 centimeters long, which is less than an inch. So if you move something even a quarter wavelength, you're changing whether it's a, a peak or a valley, destructive or constructive interference. So, okay, so how do we make it so that things are always dynamic? Well, then we introduce RF stirrers, and what's happening is these stirrers are rotating. And so during their rotation, and they're shaped differently, they're in different planes, everything like that. During the rotation, what's doing is disturbing the shape of the room enough so that over a period of time, a set period of time, you're going to see at every point in space in the reverberation chamber, or I should say mostly every point in space, you're going to see a peak and a valley at every test frequency. And the reverberation chambers have an advantage of being able to work across a really broad spectrum, or frequency range I should say, with great results. Now why
would you choose a reverb chamber over an anechoic chamber for testing, RF meters?
Right. So okay. So if we're talking about mimicking or simulating what the human body is experiencing in the world, when you're being bathed in microwave radiation in the real world in most cities right now, reality is when you're home, you're getting reflections. You're sitting in a soup, good analogy, and we're getting reflections from all over the place. So RF can be coming from your neighbors downstairs or a room upstairs if you've got a family member that's streaming some video or talking on the cell phone.
Or an apartment building from the antennas.
If you're living in an apartment building, you might have cell phone antennas on the roof, but you're going to have all kinds of neighbors, each having their own Wi-Fi and everything. So you're getting RF from all these different sources. So the engineers at this one test chamber were like, well, really, the advantage of a reverberation chamber is that you're simulating RF coming from all directions. So to their minds, more real world testing, right? So what that's called RF coming from different directions all at the same time, or ability to come, is called multipath. This is the transmitter antenna. This is the receiver or the RF meter that we're using, right? This area between these 2 points is called the path. But all of a sudden, when you have this receiving area, or your body, or somebody like me or you, in a world of RF soup, we're getting multipath, we're getting signals from all directions hitting us. So really, from when I started thinking about it, it's like, wow, it seems to me like the only way to test equipment is in a reverberation chamber, if we're testing equipment that's measuring the effects of microwave radiation. So now what are the disadvantages and advantages, right? The problems with that.
Well, so why does everyone choose to test in an anechoic chamber?
Yeah.
Let's start there.
Well, that's an industry standard. That's been used. They're more prevalent, right? It's easier to find, accessible. There's easier to find anechoic chambers. Now there is, reverberation chambers have been around for decades. The technology's been known for a long time. But I think in this kind of testing, what we've faced is that we're heading into new territory, is that there's a lot of RF meter testing manufacturers of RF meters that don't test their meters in a lab. And they make claims about frequency response and everything like that. But if you actually test them in the lab, those specifications are not necessarily true. And we've done videos on that in the past.
So when we test in the Anechoic Chamber for third-party certifications, we tend to do it in the Anechoic Chamber, and we
Yes.
find a nice, like, we make nice linear lines that we can figure out how accurate we are across the whole frequency spectrum.
Yes.
And then we get different readings than we would in the reverb chamber.
Right. So here's the dilemma. The standards for the few companies that have actually done RF testing for their consumer or prosumer, we're only aware of 2 companies that have actually, done
Or at least
published their test results. Good point. The standard is to use a anechoic chamber. We started experimenting with Reverberation Chamber just, again, because it seems to me that it simulates reality more. So we're in the process of investigating what are the differences. We're seeing lots of similarities in frequency response. We're not talking really radical differences, but the question will become is like, what should the testing standard be? Do we, and so I guess the point of this video is that we don't necessarily have an answer yet, but we believe that having test results from both a anechoic chamber and a reverberation chamber is beneficial, because it helps us understand how our meters or our devices that we make, how they respond to multipath signals. And that can be done in an anechoic chamber, but that is a completely different test. That's getting into antenna radiation patterns and things like that. And then you have to rotate and you have to it's a very, very much involved test that takes a lot more time. And again, it's largely theoretical, because as a person, are you going to always stand in the same point?
But it's kind of more, it's closer to what we can get to safely testing something that would tell us what our real bodies are experiencing.
Right. And the reverberation chamber is pretty simple. I mean, basically, if the chamber, this is a smaller chamber, but it's very, very useful for what we're doing. But especially in larger chambers with huge stirs, pretty much in a whole center area of the chamber, you can put your device under test there, and it doesn't really matter where it is. You're going to get predictable test results. And you know that the RF is coming from multiple directions. So I've said in another video, the reason you're seeing these flashes in light, you can think of it as the same way as RF, is that no matter where I am at one point in this chamber, it's very subtle right now because the lighting isn't very bright here, but over a set period of time, maybe 10 seconds, my fist area is going to get illuminated at some point. So in other words, if you think of the light in the same way as RF, wherever you are, there's going to be it's a shorter wavelength, but it's still the same thing. And the nice thing about a reverberation chamber is that there's really essentially no upper limit to the test frequency, because
the size of the waves doesn't
matter. It's the limitation, as in most chambers, is the lower frequency stuff. But it's an intriguing thing, and let's put it this way, we're on it. And construction of a small reverberation chamber that's useful for testing is a lot more, it's a lot more affordable, economically feasible is the words, but affordable is a better way to say that. And so anechoic chambers are very expensive because they have to be big, and the RF absorber tiles are extremely expensive. So you're looking typically, a useful RF for anechoic chamber is probably, it's in the 6-digit category for cost, if not in the larger chambers are in the millions, multiple millions of dollars.
7,
Right. Whereas a reverberation chamber, you can get something functioning for a lot less money, and so we're playing with it, I think, for good reason, and we're questioning and inviting other people who are interested in getting involved with the testing their products. We're engaged. Testing in general. We're interested in engaging them in conversation. It's just like, hey, going forward, the reason for us doing testing and wanting testing standards out there is to raise the bar so that the equipment that people are using to determine if RF is harmful for them, we want the equipment to be calibrated, reliable, so that it's actually showing accurate, right? Yeah,
Otherwise,
real
if it's
testing.
not showing proper numbers, then how, one, you can't trust your data, and
Yeah.
two, you can't trust the field, and three, it just kind of like snowballs into
Right. So our
a
effort,
larger issue, yeah.
our effort to push manufacturers and people in that direction, just like medical equipment, you know, demand certain accountability testing. If there is a good way to test that's more economically feasible, then that's a benefit, right? So I just cranked the speed of the stirrers, as you can see. We're going to end with a little bit
The light show.
a light show at the end. But I think that's
It makes sense to be able to, like, one, test, and then two, test affordably in something that makes sense.
yeah, and it's predictable. Like
Yeah, it has to be it's standard.
standard,
Like,
so that it can be duplicated at multiple places. That somebody can build a reverberation chamber using the same antennas for transmitter sources, come up with the same results. That's the whole idea. We want to be able to, you know.
following the scientific method, it is
Yeah.
very
Yeah.
important.
So anyway, this room, it's funny, it was an initial sort of side project, but it's actually turned out to be one of the most important rooms for us, because we get to have the benefits of a Faraday cage, but we also get the benefits of a controlled RF environment, and with the stirrers, we can do some really cool stuff here.
Anyways, thanks for cooking. Hope you enjoyed that. If you have more insight into this, please feel free to leave comments below and contact us. And thank you very much, Bruce.
Thank you, Kelly.